All right, well, welcome back to another discussion in Calculus 2. We're going to pick up kind of where we left off in the last discussion on volume via the disk or washer method, where we outline this general process, this idea of knowing your region, knowing your axis of rotation, taking a cross-section, again, perpendicular to the axis of rotation, revolving that cross-section, and determine the area, either a disk or a washer, and then integrating those areas together to generate the solid as a whole. And so we're going to go through this process and kind of work it out, flush it out through some examples, and really see it put into action. And so I started out by giving you guys a region bounded by y equals x and y equals the square root of x. This time I didn't draw it for you. And I want to revolve the region about the line y equals 2 and find the volume. So the first two steps in this process are always given to you. You have to be given a region and given an axis of rotation. We just need to know it, right? We're not allowed to choose it. We need to know what it is. We have to be given that information in order to know it. And so we have a region, we have an axis. Let's go ahead and draw it out to get a basic understanding of what this region looks like. We have y equals x, which is a vertical line, or a diagonal line that hits the origin at a slope of 1. I'm only going to draw it in the first quadrant, even though the line extends over here, because I know the next curve is the square root of x, which is only in the first quadrant. Square root of x is concave down, so it goes up a little bit, does something like this. And there becomes a very small but naturally bounded region between these two curves. Now, of course, I need to know the bounds of this region, and I need to know which one is bigger than the other one. So just like area between curves, we could do it, right? We could find the bounds. We would set the functions equal to each other, find where they cross, giving me my bounds. And if I did that, I would get 0 and 1. We did this in a previous class, previous lecture. I would also then need to figure out which function is larger, and we also did that in a previous discussion where we talked about area between curves. And we saw that the square root of x was larger than x. And so we know which function is on top. And so I'll go ahead and get rid of the unnecessary part of the graph that I don't need. I have this region bounded between 0 and 1 in the x direction, also bounded between 0 and 1 in the y direction. And we're taking this region and we're revolving it about the line y equals 2. Now, that's up here. Right? Y equals 2 is a horizontal line at 2. Now, since there's a giant gap between my region and my axis of rotation, that's going to tell me something about the type of shape I'm going to get when I revolve a cross-section. I'm going to get a washer. And so remember, we always need to then take, now that we know our region, we know our axis of rotation. In this case, it's a horizontal axis, and my center is at 2. I now need to take cross-sections perpendicular to this axis. So since my axis is horizontal, I need to cut my region at a generic vertical line. That is a generic then x value. All right, at some x value, we make a vertical cut perpendicular to the axis. So I cut my region, very small cut, very small slice, at some generic x value between 0 and 1. That would mean I need to make sure all my functions are in terms of the x variable. They already are, so we don't need to change dependencies. So that's good, like we did in the previous discussion. I then revolve the cross-section and determine the area. So when I revolve this small little cross-section, I get a kind of very thin washer. A circle with a circle removed. And now that I know what type of shape I get, I will find the area of that really thin washer. What is the area? Well, the area of a washer, again, is the area of the large circle minus the area of the small circle, where big R represents the distance from the center to the outer edge, and little r the distance from the center to the inner edge, the circle that needs to be removed. And so now we need to figure out what big R and little r are. Now, big R represents the distance from the center to the outer edge of my circle. So if I look at my picture, again, my center is at 2. My outer edge is on the curve that's farther away from the center. In that case, that would be the curve y equals x. That's the curve that's farther away from the center, the outer edge. Now, subtracting in the right order, remember we're measuring the distance between the center, so 2 to y equals x. Subtracting the right way would be 2 minus x. In the same way, the inner circle, the inner edge that needs to be removed, the inner radius would be the distance from the center, which is still at 2, to the closer circle. That edge of that circle lies on the curve square root of x. Subtracting again the right order, bigger minus smaller, would require me to do 2 minus the square root of x. Now that we know the larger and smaller radii, we can find the area of the washer. Now that I know the area of the washer as a whole for any x value between 0 and 1, I will glue all those washers together via integration as I move along the x-axis starting at 0 and ending at 1. This will now generate the volume of the solid. So again, we went through all of these steps. We knew our region, we drew it out, got an idea of the bounds, intersection points, what it looks like. We also knew our axis of rotation. I drew that as well, so we knew where our centers of our circles were, and it was a horizontal line. We then took a cross-section perpendicular to that axis of rotation. That requires a vertical cut, so dependent on x, and we didn't need to change our functions. We revolved that cross-section, that straight line, and in this case it generated a washer for me. We then found the area of that washer. We found those radii, the distances from the centers to the edges, and wrote out what the area of that washer would be in general for a generic x value, and then we integrated the areas together now to find the volume. Now if we go ahead and go through the calculation, now it's just an exercise in calculus 1. Right? Remember, it's just applications of integration. So we're not learning anything new when it comes to calculus. Calculus is everything we've already learned. It's just how can we apply that calculus. So at this step, we have all the tools necessary to finish this problem. I'll pull out pi. Remember, pi is just a constant. I will FOIL this out very carefully. Don't forget to FOIL correctly. 4 minus 4x plus x squared minus. Okay, now I need to FOIL this out. Now, again, be careful, it's minus all of this foiling, so I'll put everything after this minus sign in parentheses. So we get 4 again, minus 4 square roots of x plus x. So if I FOIL this out, first term's going to be 4 squared, last term squared gives me x, so plus x, and then 2 times these guys multiplied minus 4 square roots of x. And then also don't forget we need to distribute the minus sign. So minus 4 plus 4x, 4 square roots of x, and then minus x. That way when I distribute the minus sign, we get this. If we simplify this, right, we get 4 minus 4, so the 4's cancel. We can combine the x terms as well. We get negative 4x minus x, which is negative 5x. We have plus x squared. And then we still have this plus 4 square roots of x. So just kind of simplifying what's going on in my integral makes my life a little bit easier in the next step. Because now this is just mostly a polynomial. We have one root term, but still everything just requires the power rule. And we can finish answering this question. So now that we know this process, we can go ahead and put it to memory. And let's go ahead and finish this calculation. So we have pi times antiderivatives. So my power rule gives me x cubed over 3. My power rule gives me minus 5x squared over 2. My power rule gives me, now remember this is x to the 1/2. So when I use my power rule, we add 1 to the exponent. So x to the 3/2 over 3/2. Or then 2/3 x to the 3/2, giving me then times 4 would be 8/3 x to the 3/2, evaluated from 0 to 1. So we take that antiderivative using everything we know from Calc 1, and we evaluate it. We plug in 1, and I think about 1 to any power, it's 1. So 1/3 minus 5/2 plus 8/3 minus pi times, well, plugging in 0 again, we get 0. So there we go. And finally, we get 1/3 plus 8/3, which is 9/3. That's great because 9/3 is just 3. and then minus 5 halves times pi. We do need a common denominator here of 2, so that would be 6 over 2 minus 5 over 2 is 1 over 2 times pi, so we get pi over 2, or 1/2 pi. So if we combine everything together, again, combining my fractions, 9/3, which is 3, 3 minus 5 halves is 1/2, and pi times 1/2, so pi over 2, or 1/2 pi. And so we found the volume of this solid revolved around this axis, and again, we started out with an arbitrary region that we had to draw ourselves, an axis that was, not x or x-axis or y-axis, but some arbitrary line. We followed this process and we're able to calculate the volume. And so let's just do it one more time. And in this last example, right, we did 2 with the first discussion, we did 1 more here. In this last example, we're going to have to change some dependencies, and we're also going to have to motivate a new way to do it. Not because we're not going to be able to answer it, we will be able to answer it, the next question, but it's going to be a little bit more tedious. So in this case, just like the one before, we have a region, we have an axis. Let's understand it. So we have y equals 1 over x, reciprocal function, x equals 1, x equals 3, and sorry, I should give you one more, y equals 0, so bounded by the x-axis. So I'll draw the constants first. We have x equals 1, x equals 3, so we have vertical lines at 1, vertical line at 3, y equals 0 is a horizontal line at 0, and 1 over x. 1 over x is a reciprocal function. Now, if I look at the bounds I already have, it's going to be somewhere between 1 and 3 then. If I look at the output of 1 over x at 1, don't worry, it's not to scale, we get 1. If I look at the output of x at 3, this function we get 1/3. Now the 1 over x function in general looks something like this, right? It's an asymptotic function here and down here. We only need this part of it that's situated between my other bounds. So as a whole, we get a region that looks like this, where that curve on top is 1 over x. I'll get rid of the excess now. We have 1 over x right here. So there's my region. I also then need to know my axis of rotation. Now we're revolving this around the line x equals 3. X equals 3 is a vertical line at 3. Now part of this axis is right up against my region, and that's going to be what creates a little bit of a problem for me. And so now when I know my axis, I know my region, I need to take a cross-section. However, when I take cross-sections, we have a little bit of a problem in the setup. The problem I have comes in the fact that if I take a cross-section perpendicular to the x of rotation, well, that requires a y dependency now, right? So a generic y value. If I take a cross-section between 0 and 1/3 in the y direction, I will get a disk. Once I pass 1/3 in the y direction, if I take a cross-section up here of my region, I no longer get a disk, but I get a washer. So I have 2 different types of shapes, and since 2 different shapes have 2 different formulas, I'm going to have 2 different integrals. Part of my integral will be for all the disks to glue together, another integral for all my washers. In this case, I need to make a break at 1/3 because between 0 and 1/3, those cross-sections will always give me disks. They're right up against my axis of rotation. Once I pass y equals 1/3, this curve starts to move away from the axis and will now generate washers for me. And so we have both disks and washers. Pi r squared for disks, washers, the difference between the 2 circles. So we have 2 things we need to calculate. And ideally, we'd like to be able to do this without multiple calculations, without multiple integrals, and that's going to motivate the next process. And so let's go ahead and figure out what this big R is for the disks. Now, the disks are going to be limited to the interval for y between 0 and 1/3. Once I hit 1/3, that's when we're getting the washer. So between the y values of 1/3 and 1, so on this interval, we're getting washers. So let's find the r value, the radius, for values between 0 and 1/3. Now, before I do that, I remember that, hey, wait a minute, this is a y dependency. That means everything needs to be in terms of y. Now, these are just constants, so we'll just keep track of those. But hey, this function should not be left as y equals 1 over x. In fact, I need to change its dependency, solve for y. If I do that, I'll multiply both sides by x, divide both sides by y, and changing dependency again doesn't do too much for me, but I do have to do it, and it's x equals 1 over y. So instead of y equals 1 over x, we need to think of this as the function x equals 1 over y if I'm going to use it. All right, so that being said, now let's go ahead and measure. The radius of the discs is the distance from the center to the edge. The center, again, is at 3. That's the centers of my discs and washers. The edge is on, now in this case, a constant. Right? The edge of the disc is at the constant x equals 1. So here, the discs have a constant radius of 3 minus 1. The center to the edge, bigger minus smaller, gives me 3 minus 1. And in fact, it's always 3 minus 1, which is 2. So the radius of these discs is always 2. And so the area of the discs is 4 pi. And we see that, right? In between 0 and 1/3, there's no change, right? This is a constant here, this is a constant here, and there we go. Now, once we hit 1/3, between 1/3 and 1, if we take cross sections up here, now we have a changing inner radius, which is going to generate a different shape, a washer, and will give me something in terms of y. So again, we measure the outer radius and the inner radius, the larger radius and the smaller one, so big R and little r. Again, big R is the distance from the center to the outer edge. Now in this case, it's still, the center is 3, the outer edge is still on 1, and so just like before, the outer edge is still 3 minus 1, which is 2. Right, the outer edge is still the same throughout, whether I'm between 0 and 1/3 or 1/3 to 1, the outer edge of my circles are all the same. It's once I pass 1/3 that the inner edge of my circle now becomes a quantitative value. And so the inner edge would be the distance from the center to the inside edge of my circle. Well, that's now on this curve 1 over y. Subtracting in the right way, we'll get 3 minus 1 over y. Now that depends on y. And so what is the area of the washer? We get pi times 2 squared, just like before, minus pi times, well, 3 minus 1 over y squared. So 3 minus 1 over y squared and 2 squared. The outer radius and the inner radius, the area of the washer. Now, to find the volume, what we would need to now do is integrate these discs, integrate these washers together over the right intervals, and add them up. And so I'm going to get 2 integrals. I'm going to get the integral from 0 to 1/3 of pi times 2 squared dy, or moving along the y-axis from 0 to 1/3, plus, now we'll go from 1/3 to 1. We'll add up the washers, and the y values from 1/3 to 1. And the area of those washers is pi times 2 squared minus pi times 3 minus 1 over y squared dy. And so now we get a way to calculate this, right? Get 3 minus 1 over y squared, 2 squared, and 2 squared, right? We get these radii that we just measured. We have a way to find the volume, and let's go ahead and calculate it. Here, remember, this is 4 pi. 4 pi is just a constant. So we're just going to integrate 1 or 1 dy. Let's go ahead and simplify this really quick before we go to calculate. Get 4 pi again, minus pi times. All right, so now we have to be careful foiling this out correctly. We get 9 minus 6 over y plus 1 over y squared. That would be foiling that out. Factoring out the pi, let's go ahead and answer this one. So this is 4 pi y from 0 to 1/3. We need to evaluate. Plus, here factoring out the pi, 1/3 to 1, we get 4 minus, distributing the minus sign, we get minus 9 plus 6 over y minus 1 over y squared dy. 4 minus 9 is -5. We can combine our constants. And now we integrate. So I won't do this one yet. We'll save it for when we have the other one ready. Plus pi times, okay, now antiderivative here. We get -5y. Ooh, remember, antiderivative of 6 over y plus 6 ln of y, absolute value of y. And minus antiderivative of 1 over y squared, that's not ln, that's the power rule, so that's -1 over y, so now plus 1 over y. Evaluated from 1/3 to 1. And so now we can evaluate this. So let's go ahead and do it. So we get 1/3 here, plugging in, we get 4/3 pi minus 0. So we have 4/3 pi for the first one plus pi times, let's see, when we plug in 1, we get -5 plus 6 times ln of 1, but ln of 1 is 0. So we get 0 here for that second term, plus 1. That's when we plug in 1. And then minus pi times, okay, let's plug in 1/3. Well, here, okay, we get -5/3. Here we don't get such a nice number. What we get, 6 times ln of 1/3. And then plus 1 over 1/3, which is 3, right? So then we get a plus 3. Simplifying this, we'll just go ahead and combine what we can. Here, -5 plus 1 is -4. We have -5/3 plus 3. So we get 4/3 here. Right, -5/3 plus 3, 9/3. We get 4/3 and then a minus sign here. So we get -4/3 pi. And then, well, we distribute the minus sign, so minus 6 pi times ln of 1/3. That's what we get there. Then we need to take this and add all of this. And so what do we get? We get 4/3 pi minus 4 pi (4/3 pi minus 4 pi minus 4/3 pi minus 6 pi ln of 1/3. And so now we get the volume of the solid. And of course, if you're wondering, well, this looks a little weird because, well, the 4/3 pi's cancel. 4/3 pi minus 4/3 pi. It looks like we're getting a negative answer for volume. Now, I'll stress that this is actually not a negative answer. There's a couple ways we can think about why it's not negative. If we look at ln of 1/3, ln of 1/3 actually is a negative number. ln of 1/3 is negative, making this now positive. And -4 pi plus this amount will get me over 0. And so don't worry, this is positive, and it is a positive volume. So even though it looks scary, you're like, wait, did I do something wrong? Because it looks negative, it's not, right? ln of 1/3 is a negative number in and of itself, and negative times negative makes positive, and this is larger than 4 pi. And so it will bring me in the positive realm, and so don't worry, we calculated the volume correctly. Now in doing this, right, following this process, we had a little bit more involved of a time doing it. We had, not only did we have to change dependencies, that wasn't as fun, right? Things in terms of y wasn't difficult, but we just had to think a little bit. We then needed to create 2 intervals because we got 2 different shapes depending on where we were, where we took our cross section. generating two integrals that we need to solve. And while the integrals themselves aren't necessarily complicated, right, it's just an application of integration, so nothing new, it's just not fun because it just required a lot more work. And so what we're going to do is try to motivate now in the next discussion, motivate a new way to calculate volume. And so we're going to look at the same example in the next discussion, but what we're going to do is we're going to generate a new type of shape. Instead of taking cross sections perpendicular to the axis of rotation, we're going to change it and take cross sections parallel to the axis of rotation. It will generate a different shape for me, but it might be easier to calculate the volume. All right? And so I hope that was helpful. We'll come back and we'll discuss the next method to calculate volume, which is the shell method.